is David DeColibus. He's from New Mexico State University, and he'll be talking about the longitudinal distribution of water ice on Miranda.
Hi, everybody. Can you hear me okay?
Yep.
Okay. Share my screen here. Okay. So I'm David DeColibus. I'm a graduate student at New Mexico State working under Nancy. Most of you probably know me as one of the observing specialists on 3.5 meter. And today I'm kind of talking about what has been my dissertation work, which is basically constraining the distribution of water ice on the satellite of Uranus called Miranda. So my collaborators in this are Nancy and Richard Cartwright at the SETI Institute. So just as a brief overview, Uranian system has five major satellites. Miranda is the smallest of them. It's only about 230-ish kilometers in diameter, so it's pretty small. It's essentially roughly big enough to keep itself round, and that's about it. And it's also pretty faint. So in K-band at opposition, it's about 14.6-ish. If you're not observing around opposition, you can add another magnitude to that. So it's pretty faint, especially when compared with the presence of Uranus and the other Uranian satellites very close by. What's kind of interesting about the Uranian system is mostly that it has such extreme seasonal variation. Since its axial tilt is like 98 degrees, it is essentially at a right angle to the rest of the solar system. And so this leads to kind of very unusual effects when it comes to insolation and how much sunlight is getting received on any hemisphere at any given time. So it was essentially the only close-up look we have of Miranda came from the Voyager flyby in 1986. There hasn't been any other mission since, and so you see this kind of crater-looking terrain. That's kind of what we expected. And then there's these regions with a lot of geological activity, or like faulting and rifting and that kind of stuff, which was not expected, because we don't expect to see that on a body this small. It's not large enough to retain enough heat in order to basically maintain that kind of geological activity. But since we only have one flyby, our only real way to study it is from telescopic observations. And generally what we've been doing is through the near infrared. A near infrared spectrum gives us some diagnostic absorption bands corresponding to minerals and compounds on the surface. This is not the thermal infrared, this is just reflected sunlight. Primarily what we see in the Uranian system is water ice, carbon dioxide ice, and there's some hints of a weak absorption feature around 2.2 micron, which might be an ammonia related feature. Primarily what I'm going to be talking about today is just water ice. So if you look across the 5 Uranian satellites, we see these spatial trends in surface composition as well. So we have Uranus kind of up top. We have, this is like a top-down view-ish of a diagrammatic satellite here, where you have a leading hemisphere, a trailing hemisphere, where the leading hemisphere is the one that's kind of facing the way that it's orbiting. And these satellites are all tidally locked. And then kind of here would be kind of a sub-Uranus, and here would be kind of an anti-Uranus, quote unquote, quadrant or hemisphere. Basically what we see is that for water ice, there is more, generally stronger water ice absorption bands on the leading hemisphere compared to the trailing hemisphere. And the asymmetry between the two hemispheres gets stronger as you get closer and closer to Uranus. So the reasoning behind that tends to be because there are various physical and chemical processes that are occurring in the system. So for example, you have impacts, you have radiation, you have possibly sublimation from volatiles. You could be running into dust that's like mantling the leading hemisphere. In the case of the water ice absorption or abundance asymmetry, kind of what you would expect is heliocentric impactors, just kind of stuff orbiting around the solar system. It's going to be, you're going to find more of them closer to Uranus because it has more gravity. And the speed is going to be of a similar magnitude to the orbital velocity of the satellites. So the impacts should preferentially occur on the leading hemisphere, like a car on the highway running into raindrops. Like you're going to see a lot of rain on the windshield. You're not going to see much on the back window. And this should preferentially overturn the regolith of the leading hemisphere and expose fresh water ice. So we would expect to see more basically fresher water ice and deeper absorption bands on the leading hemisphere. And then here from a paper my collaborator put out in 2018, you can see that essentially the asymmetry between the two hemispheres gets stronger and the absorption gets stronger as you get closer to Uranus, except for Miranda. Miranda doesn't seem to show any asymmetry between its leading and trailing hemispheres at all, which is weird because we would expect to see it the strongest there. And part of that, we figured, okay, maybe that's because there's some limited data set, just because Miranda's hard to observe. It's the kind of inventory of rotationally resolved spectra on Miranda is much lower compared to the other Uranian moons because it's so much fainter. And so we basically undertook a project to start looking to try and get a good comprehensive longitudinal coverage of the northern hemisphere of Miranda. And so we used the 3.5 meter. Basically using triple spec, we acquired about 20 new near IR spectra of Miranda's northern hemisphere, in addition to 2 spectra with GNIRS on Gemini North. Here's just kind of some example of our data where kind of the absorption bands of interest are this one between about 1.5 and 1.7-ish, and then the one between about 1.9 and 2.2. So those are the 1.5 and 2.0 micron water ice bands. And so we've achieved pretty good longitudinal coverage, allowing us to kind of constrain any asymmetry in the distribution of water ice. This is basically all the spectra that existed of Miranda before, of Miranda's northern hemisphere. This is all the ones that we have now. So we achieved real good longitudinal coverage between about 45 and 50 degrees north. Unfortunately, we can't see the southern hemisphere right now because of the seasonal kind of variation on Uranus, but we have very good mapping of the northern hemisphere. And so what we're actually doing to look at it is right now we are just looking at band areas. Just integrate the band areas here. It's essentially the same as an equivalent width of the 1.5 and kind of anecdotally the 1.65, which is indicative of crystalline water ice, and the 2.0 micron band. Kind of this area here, it is part of the band, but in a lot of our lower signal noise spectra, it is so contaminated by caloric noise, we can't use it. And so what did we find? If you look at kind of longitude on the x-axis and kind of integrated band area on the y-axis here, kind of the top set of measurements is the 2.0 micron band. The bottom set is the 1.5 micron band. And then on the left panel is the band areas. On the right panel is the band depths. So if you look at the 1.5 micron band, there's this weird kind of sinusoidal pattern. We would expect to see a sinusoidal pattern, but we would expect it to be the highest in the leading hemisphere and the lowest in the trailing hemisphere. Instead, what we see is that it's the highest in the kind of anti-Uranus hemisphere and lowest in the sub-Uranus hemisphere, which is unusual. But if you look at it with the 2.0 micron band, we really don't see a whole lot of asymmetry at all. So kind of previous studies have hinted that, is there a leading trailing asymmetry in water ice on Miranda? And the answer is no. I mean, so we can confirm previous results on that with much better accuracy because we have a lot more measurements. So if you look at the ratio between the mean band areas on the leading hemisphere and the trailing hemisphere, with these are just 1 sigma errors here, like it's pretty much consistent with 1. But if we look at the anti-Uranus and sub-Uranus hemisphere, you know, there's a couple of these. This is basically exactly 2 sigma. Here it's 3. There's definitely a statistically significant difference in the 1.5 micron band, but not in the 2 micron band. We also did kind of an F-test just to compare if the sinusoidal model is a better fit statistically than just a simple mean. For the 1.5 micron band, yes. For the 2 micron band, no. So kind of why it's going to be a little bit different for these water ice bands, that is still a question that I'm looking into. But the conclusions are essentially there's no clear evidence of a leading trailing hemispherical asymmetry, which is already a result because we expect there to be one. There is evidence for a hemispherical asymmetry between the anti-Uranus and sub-Uranus hemispheres, but only in the 1.5 micron band. As for why this is, could be contamination from scattered light. There's a lot of scattered light from Uranus, especially in the 1.5 micron region, but it's essentially negligible in the 2 micron region. Could be magnetospheric effects, could be volatiles or lack thereof, could be resurfacing, mantling, polar reorientation, all of which are processes that have been, you know, expected to occur on like Enceladus, which is essentially the closest analog to Miranda, except Enceladus is currently active. We don't believe Miranda is. It's cool. It's weird. And it's coming soon to a journal near you. I'll take questions if you got any.
All right, thank you. Okay. Looks like Bryson has a question for you.
Yeah,
ahead,
great talk, David. Always fun to learn more about this stuff. I was wondering, when you're getting your, when you're analyzing your spectra, does it make sense to kind of try to model the lines to get that data that's wiped out by the atmosphere, or does it just make more sense to not try to extrapolate it out and just stick with the data that you actually are sure that you have?
So you mean as in like the continuum, like in the kind of the roughly 1.4 and 1.8 regions where it's really strong absorption?
Yeah, like if you were to divide out the continuum, you could like theoretically maybe model that absorption line and get that left wing.
Yeah, so I have tried. It's so theoretically, at least, there aren't any super important absorption features in those regions. And the absorption features that do exist on solid bodies tend to be very wide and broad. So especially when you're looking at water ice, where I'm working with a spectral resolution of 3500, I could probably do the same thing with spectral resolution of 100. But when it comes to modeling that stuff, there is radiative transfer modeling of kind of how light reflects off particulate surfaces. That is kind of future work in this case. Right now, I'm just focusing on analyzing the real basics of the kind of absorption band areas, but I will do that. But when it comes to, but also when it comes to modeling like telluric absorption, I've put a decent amount of work into that, and I've never been able to get decent results compared to just observing standard stars frequently and dividing them out that way.
Cool, thanks.
Okay. Yeah. All right, we're going to go ahead and move on to the next talk. If there are any other questions for David or Adam, please feel free to put them in the Slack or in the chat for them. Let's go on to our next speaker. Mikhail, yeah, great job. Thank you, David. Yeah. Our next speaker